The learning outcomes of this module are: you would know about PTC reactions, you would learn kinetics and the reaction mechanisms of PCT reactions, you would be able to identify the use of these reactions, and we will be analyzing Hofmann elimination, Stevens rearrangement, Michael addition and Heck reaction. Let us start by the introduction. Since its introduction around 1965, phase transfer catalysis, abbreviated as PTC, has become a firmly established technique in synthetic organic chemistry. Most of the work has been done on synthetic methods using PTC, but one of the major concerns in using a PTC in soluble form is its separation from the reaction mixture. For efficient use of the catalyst and to meet product purity requirements, synthetic techniques using PTCs involve an additional separation for catalyst isolation and product purification. In 1971, Charles Starks introduced the term phase transfer catalysis, that is PTC, to explain the critical role of tetraalkyl ammonium or phosphonium salts in the reactions between two substances located in different immiscible phases. Now let us have a look at PTC reactions. There are many desirable reactions which cannot be brought about because the reactants are inaccessible to each other. The crucial difficulty of bringing together a water-soluble nucleophilic reagent and an organic water-insoluble electrophilic reagent has been traditionally solved by the addition of a solvent that is both water-like and organic-like. The transfer rate is very high by increasing the area of the interface. PTC is a well-known method for promoting reactions between reagents with opposite solubility preferences. In such systems, each reactant is dissolved in the appropriate solvent. Commonly, the two solvents are immiscible to one another, and then a PTC is added to facilitate the transport of one reactant into the other phase. For instance, the displacement reaction of 1-chlorooctane with aqueous sodium cyanide is accelerated many thousand-fold times by the addition of hexadecyl tributyl phosphonium bromide as a PTC. The key element of this tremendous reactivity enhancement is the generation of quaternary phosphonium cyanide, which renders the cyanide anion organic soluble and sufficiently nucleophilic. Although this was not the first observation of the catalytic activity of quaternary ammonium salts, the foundations of PTC were laid by Starks together with Makosa and Brandstorm during the mid to late 1960s. Ever since that time, the chemical community has witnessed the steady growth of PTC as a practical methodology for organic synthesis, featuring its simple experimental operations, mild reaction conditions, inexpensive and environmentally benign reagents and solvents, and the possibility to conduct large-scale preparations. Nowadays, PTC appears to be a prime synthetic tool, being appreciated not only in various fields of organic chemistry, but also among widespread industrial applications. Despite the development of PTC in organic synthesis, the mechanistic aspects of PTC remain obscure due mainly to the difficulty of investigating biphasic systems and the many complex parameters that must be analyzed. Next, let us analyze the principle of phase transfer catalysis. The principle of PTC is reported by Rubin and Joberg in 1981. The principle of PTC is based on the ability of certain phase transfer agents called PT catalysts to facilitate the transport of one reagent from one phase into another immiscible phase, wherein the other reagent exists. Thus, reaction is made possible by bringing together the reagents which are originally in different phases. However, it is also necessary that the transferred species is in an active state for effective PT catalytic action and that it is regenerated during the organic reaction. There are many types of PTCs such as quaternary ammonium and phosphonium salts, crown ethers, cryptons, etc. Among these, the quaternary ammonium salts are the cheapest and hence the most widely used in the industry. Despite the development of PTC in organic synthesis, the mechanistic aspects of PTC remain obscure due mainly to the difficulty of investigating biphasic systems and the many complex parameters that must be analyzed. Now let us see the mechanism of PTC. According to Starks, a quaternary ammonium halide dissolved in the aqueous phase Q plus X minus undergoes anion exchange with the anion of the reactant dissolved in the aqueous solution. The ion pair formed, that is Q plus X minus, can cross the liquid-liquid interface due to its lipophilic nature and diffuses from the interface into the organic phase. This step is called phase transfer. In the organic phase, the anion of the ion pair is nucleophilic and it undergoes a nucleophilic substitution reaction with the organic reagent, forming the desired product Ry. The catalyst subsequently returns to the aqueous phase and the cycle continues. We have a graph here which shows us that the organic phase is there and the aqueous phase, and then we have the interfacial region which forms the boundary, which is actually the geometrical boundary between the two phases and which is crossed over, is the representation of the interfacial region between two mutually immiscible phases in which there is a gradient of concentrations. Curve O and A represent concentrations of components of organic and aqueous phases respectively. An overview of PTC reaction is given in the scheme. We have the aqueous phase which contains Qy, which crosses over through the interface into the organic phase. There the reaction takes place. We get Ry and Qx. The Qx is again, it crosses the interface and is transported back to the aqueous phase, and thus the cycle goes on. The phase boundary between these liquid phases should be rather termed the interfacial region and defined as a region of contact of two mutually immiscible phases, where due to the molecular motion there is a gradient of concentration of components of these phases as shown. An example for PTC reaction is as follows. If the primary chloride is used, only the SN2 reaction normally occurs, so that once again we get nucleophilic attack at the primary center, and the more stable product with a more highly substituted alkene. This example is interesting because the starting material contains an acetal as well as a primary alcohol group. Acetals are very easily destroyed by acid, so the conditions must be kept strictly alkaline. NaOH does this, but it is insoluble in the organic solvents. The method shown here uses a two-phase system of water and dichloromethane, that is DCM or CH2Cl2. The organic molecules are in the DCM layer and the NaOH is in the water layer. As you can see, the tetraalkyl ammonium salt has a polar group N plus and the hydrocarbon side chains, that is the butyl groups. The ammonium salt allows a low concentration of hydroxide ion to pass into the DCM layer where they act as a base catalyst for the reaction. This method is called PTC because the tetraalkyl ammonium salts act as a PT agent, allowing ions to pass into the organic phase. The ether product is of course soluble in the organic phase and the workup is very simple: separation of the phases. It removes unchanged NaOH and the inorganic byproduct NaCl. Next, let us talk about inorganic base promoted activation of acidic organic compounds. The representative reaction system applied in asymmetric PTC is a biphasic system composed of an organic phase containing an acidic methylene or methine compound and an electrophile, and an aqueous or solid phase of inorganic base such as alkaline metal, which could be sodium, potassium or cesium hydroxide or carbonate. The key reactive intermediate in this type of reaction is the onium carbanion species, mostly onium enolate or nitronate, which reacts with the electrophile in the organic phase to afford the product. Generation of reactive onium carbanion species. The exact pathway for generating the reactive onium carbanion species remains the subject of controversy, typically among Stark's extraction mechanism and the Marcorza interfacial mechanism. In the Stark's extraction mechanism, the PTC moves back and forth across the organic and aqueous phases. The onium salt equilibrates with the inorganic base in the aqueous phase and extracts hydroxide into the organic phase. The onium hydroxide then abstracts hydrogen from the acidic organic compound to give the reactive intermediate Q plus R minus. The advocated pathway of the interfacial mechanism is the first formation of metal carbanion at the interface of organic and aqueous phase in the absence of PTC, followed by the extraction of the formed metal carbanion species from the interphase into the organic phase by the action of PTC. Since asymmetric PTCs normally contain highly lipophilic chiral organic frameworks and are reluctant to enter the aqueous phase, the Marcorza interfacial mechanism seems possible. Clearly, the area of the interface and the basicity of the inorganic salt affect the amount of available onium carbanion. It should also be noted that an excessively lipophilic PTC would hardly access the interface, and consequently the use of such a catalyst would result in an insufficient reaction. Here we have the diagrammatic representation of the Stark's extraction method and the Makosa interfacial mechanism. Next, let me talk about the stability of the onium carbon ion. The onium carbon ion formed under PT conditions is unstable depending on the anion source, and in the absence of an electrophilic reaction partner, degradation of the accumulated onium carbon ion in the organic phase may be observed. This is known to proceed via Hofmann elimination, nucleophilic substitution, or Stevens rearrangement. The direct decomposition of onium salt as influenced by the strong inorganic base at the interface may also be operative. Reactivity of the onium carbon ion. Cation exchange from the metal cation to the onium carbon ion improves the intrinsic reactivity of the latter due to formation of the naked anion. At the same time, the onium carbon ion in the organic phase is less hydrated compared to the metal carbon ion at the interface, which functions as another factor for an enhanced reactivity of the onium carbon ion. We have the diagrammatic representation of Hofmann elimination and nucleophilic substitution. You can see the product formation. Next, let us talk about nucleophilic substitution reaction. The fate of the onium carbon ion, that is Q plus R minus, incorporated into the organic phase depends on the electrophilic reaction partner. The most studied area in the asymmetric phase transfer catalysis is that of asymmetric alkylation of active methylene or methene compounds with alkyl halides in an irreversible manner. The reaction mechanism illustrated above is exemplified by the asymmetric alkylation of glycine Skiff's base. The reaction is shown. In the first step, glycine Skiff base 2 reacts with the inorganic base 1 at the interface of two phases to give the metal enolate 3, which remains at the interface due to its highly polar character. The metal enolate 3 then exchanges the cation to provide onium enolate 4. The sufficiently lipophilic 4 then moves into the organic phase to react with alkyl halide. After the reaction, onium halide is regenerated and enters the next catalytic cycle. The key issue to be considered here is the possibility of product racemization and dialkylation. In this example, the basicity of the inorganic base and acidity of substrate and product, as well as other reaction conditions, are carefully adjusted to circumvent this problem. It should also be noted that control of the EZ geometry of the enolate is apparently critical to the asymmetric induction. Although there is no clear evidence about which isomer is the actual reacting species in this case. An asymmetric SN2 reaction and SNAR reaction are included as other examples of this category. Nucleophilic addition to electrophilic double bonds. Unlike the nucleophilic substitution reactions which generate stable onium halide after the reaction, nucleophilic additions to electrophilic C double bond X, where X could be an N or an O, provide rather basic onium anion species as an initial product. If the anion is sufficiently stable under the reaction conditions, onium anion will then exchange the counter ion for the other metal carbon ion at the interface to regenerate the reactive onium carbon ion, that is Q plus R minus. In another scenario, the basic onium anion may abstract the acidic H atom of the other substrate to provide Q plus R minus directly. Such a reaction system ideally requires only a catalytic amount of the base, although in general a stoichiometric or excess amount of the base is used to lead the reaction to completion. An additional feature of this system is the substantial possibility of a retro process at the crucial asymmetric induction step, which might be problematic in some cases. The direct asymmetric aldol reaction under PT conditions is a representative example of this class of PT reaction, which is known to proceed with a catalytic amount of base and to include an undesired retroprocess. The PT catalyzed asymmetric Michael addition and the Mannich reaction are other typical examples which fall into this category. Next, let us study about phase transfer catalyzed addition of anion supplied as metal salt. The common feature is the asymmetric PTC introduced above is formation of the reactive onium carbon ion from the inorganic base and active methylene or methine compounds, followed by extraction of the carbon ion species as the onium salt from the interfacial area into the organic phase. Thus, both reagents normally remain in the organic phase. In the other category of asymmetric PTC, the anion itself supplied as an aqueous solution or solid of its inorganic salt as the reaction partner, and the two reactants are strictly separated by the interface. In such a system, the anion is transferred gradually from the aqueous phase into the organic phase by the intervention of an onium salt. With regards to the mechanism of the generation of onium anion, the Stark's extraction mechanism and interfacial mechanism, Brandstrom-Montanari modification, have been suggested. As in the described case, the interfacial mechanism seems to be operative in the asymmetric PTC. The reaction conditions are rather mild, so that the possibility of side reactions such as catalyst decomposition is considerably reduced. The major challenge associated with these reactions is an absence of prochirality in the anionic species. Namely, the chiral onium anion must discriminate the enantiotopic phase of the distant electronically neutral reaction partner in the organic phase. Asymmetric PTC oxidation of olefin using sodium hypochlorite or potassium permanganate as metal anion sources is the typical example of this category. We have an example here where the asymmetric epoxidation of an alpha beta unsaturated ketone has been shown. Hypochlorite is extracted as an onium salt into the organic phase, and the onium hypochlorite then reacts with the ketone, which recognizing its enantiotopic phase to provide the optically enriched alpha beta epoxy ketone. Use of crown ether as phase transfer catalyst. Crown ether is the other important class of PTC which critically differs from the onium salt in that the whole inorganic salt is transferred into the organic phase. The reaction modes described above can generally be accommodated in such crown ether catalyzed reactions simply by replacing the onium cation by a metal cation complex of crown ether. Next, we'll talk about the kinetics and interfacial phenomena in PTC reactions. Small amounts of PTC in extremely slow reactions between components existing in two immiscible phases are usually sufficient to accelerate them. This capability strongly depends upon A. The distribution equilibrium of the PTC in the two phases, B. The mass transfer rate between the immiscible phases, and C. The reaction rate in the organic phase. The distribution of quaternary salts and their surface activity near the interface between the two media is a critical factor for the reaction. The interfacial area depends on the rate of stirring and affects the position of the extraction equilibrium of the ion pairs. Kinetics and mechanism in homogeneous PTC under vigorous agitation conditions have been reviewed. The reaction rate strongly depends on the distribution ratio as given. Here Q plus is the counter ion, Y minus is the nucleophilic anion, KEXQY is the extraction constant, and DQY is the distribution ratio of the ion pair Q plus Y minus. Thus, the distribution ratio depends on the concentration of Q plus and the extraction constant KEX. The reaction mixture requires a minimum stirring speed to achieve optimum phase contact. Under these conditions, it is assumed that the phases are in equilibrium with each other. In this vein, the rate of the overall reaction is controlled by the reaction in the organic phase, which is a pseudo first order reaction, having rate equal to K absorbed concentration QY in the organic phase. The solvation of polar analytes by water molecules in polar solvents affects the anionic reactivity significantly. The extraction behavior of various quaternary salts in the presence of NaOH based on their respective distribution data from aqueous solution to DCM or chlorobenzene. In triphase PTC, there are various parameters affecting the overall behavior of the reaction. Ion exchange kinetics, mass transfer of reactants in the bulk aqueous and organic phases, as well as diffusion of reactants within the catalyst are seriously considered. It is commonly suggested that the ion exchange reaction is very fast and thus is always in equilibrium. As a result, the mass transfer of reactants, the intraparticle diffusion of reactants, and the intrinsic organic reaction rate at the active sites determines the reaction rate. Research studies have assumed that this kind of PTC reactions have as rate limiting step the intrinsic reaction rate at the catalyst active sites. The overall rate of reaction between an organic substrate Rx and an inorganic nucleophile Y minus to form organic product Ry in the presence of triphase catalyst Qx depends upon the concentrations of Rx and Q plus Y minus. The rate law is as given. Here Rx organic is the concentration of the reactant in the organic phase and Q plus Y minus S is the concentration of the ion pair of nucleophile in the catalytic sites. Next, we have a few examples of PTC reactions. We start with Michael addition, which has been carried out using in a 10 to 40 hour reaction using 10 mole percent CPTC and 50% KOH aqueous. Then we have our second example that uses 18 crown 6 as a PTC catalyst. Our third reaction uses TBAB to get the product. The fourth example uses again TBAB in toluene solvent. As our fifth example, we have the synthesis of verapamil using PTC. The sixth example uses KMNO4 in presence of DCM to get the product. The seventh reaction uses the synthesis, is for the synthesis of mycyclobutanil using PTC. The eighth reaction uses TBAB. The ninth reaction again uses TBAB, giving us 68% yield. The 10th reaction is for PTC used in the HEC and related reactions, again using TBAC DMF solvent, giving us 94% yield. Now, to summarize what we have learnt in this module: 1. Applications involving the use of a co-catalyst include co-catalysis by surfactants, alcohols and other weak acids in hydroxide transfer reactions. Use of iodide, traditionally considered a catalyst poison, has been also reported. Secondly, in nucleophilic substitution reactions and in reactions in the presence of bases involving the deprotonation of moderately and weakly acidic organic compounds. Thirdly, we learned that PTC has made possible the use of cheaper and easily available alternative raw materials like potassium carbonate and aqueous NaOH solution, thereby obviating the need of severe anhydrous conditions, expensive solvents and dangerous bases such as metal hydrides and organometallic reagents. When any kind of chemical reactions are carried out in the presence of a PTC in biphasic systems, simple, cheap and mild bases like NaOH and K2CO3 can be used instead of toxic alkali metal alkoxides, amides and hydrides. Next, we learned that PTC can also be used for the synthesis process for fine chemicals manufacturing, as in agrochemicals, pharmaceuticals, dyes, papers, etc. It also is used in perfumery and fragrance industry, like in the synthesis of phenyl acetic acid, an intermediate in perfumery industry. Next, we learned that in the field of pharmaceuticals, like synthesis of various drugs like cyclopamine, phenopyridine and oxalizine, Ritalin, etc., PTC is used. However, the main disadvantages of PTC, especially in commercial applications, are the need to separate the catalyst from the product organic phase.